Okay, folks, let's keep plugging away. Section 11.8, vectors. We're on page 4 now. And this is specific to vector applications. And this, what you see in the gray box here is a procedure that I put together last year just because students really struggle with these problems because there's a couple different things going on and hard to differentiate between the different vectors and how they combine to get your final answer. So what I've done is tried to set up a procedure for you to follow where I start by defining the three different types of vectors that we could encounter. First thing is a true vector, and that's the vector that you either want to achieve or actually achieve after adjusting for wind or water. And then we have a vector that I label W, which is the vector of the fluid in which an object travels. This is the velocity of a water current for a boat or the velocity of the wind for an airplane. And all of these problems, these application problems, are going to have to do with the velocity of boats or planes either in water or air. Let's hope the boat is in the water and the plane is in the air. Last but not least, we have other vector, and I didn't know what else to call it, so I just called it other vector. It's the vector that adds with W to get T. So it's the vector that you add with the wind or water vector to get your true vector. And this is the equation we're going to use throughout the vector equation where the vector V, other vector, plus the wind or water vector gives you your true vector. Okay. So now let's talk about the procedure. I've identified a set of steps here that I'll read through quickly, but the one thing I want to talk about here in the first one is it says use R equals D divided by T to determine any needed speeds. Remember from back in a general physical science course that this means rate equals distance divided by time. Okay, and there might be an occasion or two where you need to rearrange this and use distance equals rate times time. That's pretty basic, and I expect at this point in your academic career you can do a problem like that without me spoon feeding it. Okay, so you're going to determine any needed speeds by using this relationship here, rate equals distance divided by time. Then you're going to identify the two given vectors and the answer vector. Okay, you have to be given two vectors, two out of these three, in order to do these problems. Then the answer vector is the one that they're asking for. And you're going to specify those vectors in terms of the names that I've given, V, W, and T. Then, for these problems, I've kind of given you a template to work with. Sketch each vector separately in standard position. Make sure your angle is measured from the positive x-axis. So you'll see that I've given you space in these problems to do that. I've given you the space to draw each of those vectors, V, W, or T. Then you're asked to write the component form of each vector in the template for V plus W equals T. And here's the template. So figure out what the component form is of the two vectors that are given and put them in the appropriate places here. Then identify the answer vector by solving the equation V plus W equals T. And last but not least, make sure you answer the question that is asked, because sometimes the final answer is not necessarily a vector. Okay, so let's jump right into an example problem here. A jet ski is traveling 75 degrees north of east at a constant speed of 43 miles per hour. The water is moving at a rate of 12 miles per hour due east. What is the true velocity of the jet ski? So you need to think of this problem in the following terms. The jet ski driver is traveling at a heading of 75 degrees north of east at a constant speed of 43, but the water is pushing him to the east at 12 miles per hour. So the other vector in this case is 75 degrees north of east at a constant speed of 43. So one thing I'll mention here is notice that in this problem I didn't give you the bearing as you're used to seeing it. It doesn't say north 75 east, it says 75 degrees north of east. So that picture is going to look like this. The 75 degrees is measured from the x-axis up to the vector, and the magnitude of that vector is 43. So you are given the other vector in this problem, V. You're also given the water vector. You're told that the water is moving at a rate of 12 miles per hour due east. Now, it's pretty easy to figure out the component form of the water vector. The water vector has a horizontal component of 12 and a vertical component of 0. Now, before we talk about anything else, I'd like to just mention one thing. In this problem, you're given the vector v and the vector w. You're asked to find, well, you're asked to find some information about that, the true vector, the adjusted vector after you account for the water current. But before I do that, I actually need to know the component form of v, so I'm going to do that calculation down here. V is going to be equal to 43 times the cosine of 75 degrees. That's the horizontal component. The vertical component will be 43 times the sine of 75 degrees. And when you plug and chug that into your calculator, you're going to get the following. You're going to get a horizontal component of 11.129 and a vertical component of 41.535. Now let's not be too sloppy here. This is the vector v. Its magnitude, or its units are miles per hour, because that is the velocity that we're working with, miles per hour. So I'm going to go ahead and fill in my template here with the vector v. I have 11.129 as the horizontal component and 41.535 as the vertical component. From here, I can go ahead and add these two vectors, v and w, to get the true vector t. And the horizontal component will be 23.129, and the vertical component will be 41.535. Okay, so let's go back and read the question and make sure we're asking the question that has been answered. What is the true velocity of the jet ski? Well, here it is in component form, but let's go ahead and give it in terms of a magnitude and a direction. So the magnitude of t, heads up, the magnitude of t is going to be equal to 23.129 quantity squared plus 41.535 quantity squared, and then we have to take the square root of that. That is approximately equal to 47.541 miles per hour. Okay, so that is the magnitude of my true vector, or the magnitude of that's actually the speed. The magnitude of velocity is speed. So that's the speed of my jet ski when I account for the water current. Now how about the angle? Well, it might make sense to take a little quick look at the sketch of this vector. I have a horizontal component of about 23, a vertical component of, when I round up, to 42. So that's going to be a vector that looks like this. And that angle theta is in quadrant 1. So I can find theta by doing the inverse tangent of the y component, 41.535, divided by the x component, 23.129. Make sure your output is in degrees, and that turns into 60.9 degrees. So theta is 60.9 degrees. If I want to report that as a bearing, so remember this is north and this is east, so this angle right here would be the bearing angle. So if I do 90 minus 60.9, I get a bearing of north 29.1 degrees east. And that's the answer to the first part of this problem. The velocity, the adjusted velocity of the jet ski is 47.541 miles per hour at a bearing of north 29.1 degrees east. Now let's see if there's anything else we were asked to do. Well, let's take a look. Oh yeah, how far has the jet ski moved horizontally and vertically after 12 minutes? So I do have more work I have to do here. What I have to do is calculate something that we'll call displacement. And for you physics folks, displacement is a change in position. So we're going to have a change in horizontal position. We're also going to have a change in vertical position. And this is where we're going to borrow some of what we've learned in the past. Don't forget, distance equals rate times time. And it says after 12 minutes. So everything else is in miles per hour. So let's convert this 12 minutes to hours. That's going to be 12 divided by 60 hours, which is 1/5 of an hour, or 0.2 hours. So we're going to need those relationships for this problem. So our displacement in the horizontal direction is going to be rate, which was 23.129 miles per hour. That's the horizontal component of velocity, times 0.2 hours. Our units of hours will cancel, and we will get an answer of about 4.6 miles. And for this, I'm just going to round to the nearest tenth, because that makes sense if we're talking about a jet ski traveling over water. You'll have to be careful with WebAssign and use however many decimals they ask for. My displacement in the y direction, or change in position in the y direction, is going to be 41.535 miles per hour, and that's the vertical component of my velocity. And I'm going to multiply that by 0.2 hours. My hours cancel, and I'm left with a quantity of 8.3 miles. So after 12 minutes, the jet ski travels a total of 4.6 miles in the horizontal direction and 8.3 miles in the vertical direction, or east and north if we're going back to the cardinal directions. Okay, so I think we've completely answered that question. That's great. We're ready to move on to 2 more examples.